Okay, everyone, we'll get started again in the Ceres and Vesta 10th Anniversary Dawn Special Session. The next talk will be on elemental composition of Vesta and Ceres by Tom Prettyman and co-authors.
Okay, thank you, Carol. I'll get started. I'm going to talk about the elemental composition of Vesta and Ceres. I'm going to summarize our results of the gamma ray and neutron detector investigation and the implication for the formation of these objects. So if you're going to invite me to an anniversary launch celebration, I'm going to show you pictures of the launch that happened a decade ago. There's the Dawn team standing in front of the gantry with the rocket about a month before launch. And here is the night before launch. It's a beautiful picture. I'm sure you really like it. To give it a feel, imagine being bitten by millions of mosquitoes. And that's about the experience you have here. But the best part is launch. And Dawn launched on early in the morning on September 27th. And here we are 10 years later, and we have lots of exciting results that we've found. So for the gamma ray and neutron detector, which measures elemental composition, we actually have measured 3 bodies. We've measured Mars, and we use Mars as kind of a reference point for the analysis of the other bodies. And of course, at Vesta, we discovered evidence for exogenic hydrogen, and we strengthened the link between Vesta and the HED meteorites. Grand was part of that. And at Ceres, we discovered extensive deposits of water ice in the subsurface and evidence for chemical differentiation. So just to make it clear, Dawn's instruments sense different depths and different spatial scales. So the Veer and framing camera sense the topmost micron or so of the surface. Grand actually senses the subsurface to depths of about 1 meter. And the way we get the sensitivity is we're looking at secondary particles from the interaction of galactic cosmic rays with the surface. And here's a typical interaction shown. It's a proton interacting with the surface, producing a spray of particles. And these particles escape the surface and they reach the spacecraft where they're detected. So Grand's sensitive to the topmost meter of the surface, and you can get specific elements from gamma rays and general parameters like neutron absorption and atomic mass, as well as other specific elements such as hydrogen and carbon from neutrons. There's Grand itself, 21 sensors for gamma rays and neutrons, and here's a gamma ray interaction. And the idea with Grand is to get the measurement, you need to be in close proximity. So at each body, Dawn's orbit was designed to get up close. In fact, for acquisition of Grand data, we need to be inside about 1 body radius of altitude from the target. Grand does not have a lens, it's not collimated, it's omnidirectional. That means it's going to have blurry spatial resolution. So with Grand, you're looking at kind of regional scale measurements. So just to start out, to provide yet more context, here's a plot of objects in the main asteroid belt. We have orbital inclination versus distance from the sun. And of course, we have some of the objects are colored according to their spectral taxonomy. And we have C-complex bodies, which are supposed to be volatile rich, and S-complex, which are supposed to be volatile poor. Vesta and its family of Vestoids are volatile poor. Whereas Ceres and other outer asteroid belt objects are volatile rich. And so Vestoids, just notice that these are probably objects that have been knocked off Vesta somehow, and chips off these are perilously close to these resonances and can be flung into the Earth where they become meteorites. Ceres, as has been pointed out several times, does not have its own class of objects, nor does it have any identified meteorites. Ceres, being water-rich, probably formed outside of the snow line in the early solar system, and that's the point where silicates and water ice together condense to form planetary bodies. So one of the things we're doing on Dawn is trying to find the hidden snow line. Where is it? And it may be present in many locations. There's evidence for objects that are comet-like in the outer belt. And there's evidence for ice on the surface of some of these bodies. And of course, there's localized ice on Ceres. And we have plumes of water vapor detected near perihelion, as was discussed in the last talk. So let's start with Vesta. It's well known that Vesta is linked with the achondritic meteorites, the HEDs, Haradite, Eucrite, and Diogenites. These are basalts. They come from the crust of a differentiated body, a body that's melted and then cooled to form an iron-rich core, ultramafic mantle, and basaltic crust. And the link, at least initially, is that you have this beautiful match between reflectance spectra, as seen by a telescope, and that which you have from the meteorites themselves. And as I pointed out earlier, when you look at Vesta up close, you see huge impact basins. And these impacts can account for the morphology of Vesta and also might have produced the Vestoids. So let's look at some data. These are petrologic maps of Vesta. So you're looking at, in this case for Grand, the percentage of eucritic materials in Haradites. And this is how they're distributed over the surface of Vesta. And in the case of Vir, there's a petrologic index that allows you to identify the different rock types within the HED suite. So Vesta, as seen by both of these instruments, is largely consistent with what we would expect for Vesta's regolith, namely Haradite. It's a regolith breccia. In addition, you have elemental signatures, such as the potassium to thorium ratio, which I've plotted now for all the inner solar system objects, and Vesta by dawn. And you can see that Vesta's potassium to thorium ratio is a really nice match to that of Haradite. So one of the things that we did not quite expect to see was so much hydrogen in the regolith of Vesta. And here's hydrogen by Grand, and it's being compared to hydroxyl by Vir. And what you can see is that hydrogen ranges from low to high. This is kind of a lower bound, but it's 400 micrograms per gram. And that's just too much for solar wind deposition alone. And there are many lines of evidence that indicate that these high concentrations of hydrogen and hydroxyl, are due to the infall of carbonaceous chondrite impactors, which contain phyllosilicates. Beautiful comparison between the two instrument data sets. Now we go to Ceres, you're never going to see this again. So at Ceres, we need to think about how water affects things. So Ceres probably formed from silicates water ice. There's enough heat to melt the water ice. The water ice interacted with the silicates, producing serpentization, and you end up with a solid residue type material, which consists of unaltered and altered components, including phyllosilicates, and then a brine, which contains salts. So you've got a liquid here. And because serpentization is highly exothermic, you can imagine that once the process starts, it doesn't stop. And you get a pulse of serpentization that propagates through the body. And so you end up with a ball of phyllosilicates. So the poster child for this kind of thing, at least in terms of meteorites, are the aqueously altered carbonaceous chondrites like Orge. And these are highly altered materials, lots of phyllosilicates and organics. And the cool thing about them is that even though they're highly altered, they have nearly the same composition as the solar photosphere. That means that the alteration happened in a closed system. And the connection I'm making here is the solar photosphere is the best analog we have to what the primitive solar nebula was made of. So this is closed system alteration on a small body. The other end member is ice rock fractionation, where you actually had the brine separating out from these solids. This is really important to keep this in mind. And we can test this kind of model just by measuring the surface composition of Ceres, measuring the elemental composition, and comparing it to the reference case, which are the CI chondrites. And if our composition matches, then we had this closed system alteration, just like the meteorites. If not, then we might have ice rock fractionation. So just to really quickly summarize, because others will talk about it, Ceres does have a lot of evidence for alteration on the surface. And you do have localized deposits of superficial ice, and you have organics in some locations. And globally, the optical surface is covered with ammoniated clays and other OH-bearing species. Let's look at that. So let's first of all compare gamma ray spectra between Vesta and Ceres. And here's a gamma ray spectrum that's been modeled for model compositions, howardite and Ci chondrite. Howardite represents Vesta, Ci chondrites represent Ceres. These are just analogs, they're not the actual compositions. So you've got counts versus pulse height, and here are some of the spectral components that go into making that spectrum. And here are the actual measurements. And what's kind of cool is if you look back and forth between these, you can say, oh yeah, I see spectral changes in the data that are similar to the analogs. Now if we actually analyze the data, and what we're doing is analyzing the ice-free part of the regolith, which we'll get to in a moment, you find out the Ceres has a carbon-bearing hydrogen-rich regolith. The potassium concentration is between the Ci and Ci chondrites. Iron has lower concentration than that of the Ci chondrites, but higher than Vesta, and the iron-silicon ratio is basically chondritic. And then finally, we have other elements that we've bounded, like iron to nickel, which are consistent with chondrites. Okay, so far so good. So now what I'm going to do is I'm going to take the two best measurements I have and compare them to the meteorites, and these are iron and hydrogen. So let's have a look at that. Here's the distribution of hydrogen. On the top you have hydroxyl, that's OH, as measured by Veer. You have this beautiful distribution over the surface, and on the bottom, oh no, they don't match. They're grossly different. And in fact, if you smooth the Veer data to the resolution of Grand and you make a scatter plot, that's a correlation that only a space physicist could love. So. And the other difference is the dynamic range of the measurement. 50% for Grand, 8% for Veer. Something's wrong. So you get 16% water equivalent hydrogen at the equator, 30% at the poles. First guess is going to be water ice. And hydrogen can be in the form of a variety of minerals, but the mineral range just doesn't get you to 29%. So the other thing you can do is you can take the distribution, a map of iron. Here's iron ranging from 13 to 17% on the surface of Ceres. And you can make a scatter plot of that. And that's anti-correlated. And that's just exactly what I would expect to happen if water was diluting out iron-bearing minerals on the surface. So in all likelihood, we're looking at an ice table. So our model for Ceres for this funny distribution axially or with latitude is that we have a receding ice table, and we've modeled that, we've compared the models to the data, and we conclude that we can actually constrain some of the thermophysical properties of the regolith, namely that the regolith has low diffusivity compared to other planetary analogs and about 10% water ice, and that the equatorial region is completely free of ice to depth sensed by Grand. That's cool, because that's a place where you can go to compare with Ci chondrites that have no ice. Okay, so this is what I'm going to do to wrap things up. The question is, do we have ice rock fractionation? Simple answer is that if hydrogen and iron kind of match up with the meteorites in the equator, we're good. We have closed system alteration, no ice rock fractionation. If not, then probably something funny has happened on Ceres. So here is the meteorite data. I've got Ci and Cm chondrites plotted, two different types of analyses, mass spec and thermogravimetric analysis. You've got iron versus water equivalent hydrogen, and these are rocks. And what you can do with these rocks is, because the rocks are absorbing the water during serpentization, is you can make an iron dilution trend. And the idea is that, yes, the serpentine upper limit is about 13%, yet the Ci chondrites have more. Well, they also have organics in them. So this water trend isn't quite right, but it's close enough for our comparison. So if I plot Ceres, if it falls on this line, within this cloud of points, then I might not be able to conclude anything about ice fractionation, but the bottom line is that it doesn't plot on the line. It's lower than the line. It's outside of the space sampled by the meteorites. And so probably you've had some sort of modest fractionation. There are uncertainties that we've analyzed, but the best fit is this data point here, and it's consistent with, if you wanted to take a meteorite composition and make this point, you would have to add something like organic matter. or bound water or some other hydrogen-rich species to get there. So I'm going to conclude for Ceres, the bottom line is Ceres it's hydrogen-rich. It probably formed outside the snow line, and you made liquid water in the interior. The ice-free regolith composition is somewhat different than the meteorites, which indicates that Ceres experienced some ice-rock fractionation, some chemical differentiation in its interior. It's not a homogeneous blob. And then endogenic water is near the surface at high latitudes. This confirms decades-old predictions by Finelli and Solvale. And of course, given this observation, you wonder, could ice be buried on other objects? And I'm going to leave you with a comparison between Vesta and Ceres. Vesta, of course, being the dry end member, Ceres being the wet end member, Vesta having exogenic hydrogen, and Ceres having hydrogen from within. And I'll thank you for your attention. Oh, I'm way over.
Okay, I'm sorry, there's no time for questions.
Okay.